And that is a striking formula. In fact, as far as I know, it's the first formula ever written down in physics that involves both h bar and g. H bar, quantum mechanics, g, gravity. The big unsolved problem or ongoing project in high-energy theoretical physics is quantizing gravity. And now we have an equation in which both h bar and g appear. And so this is like the most, this is in some sense the first quantum gravity equation, and it's telling us something quite profound. Okay, so there's some historical story in which Bekenstein wrote this formula down, and then Hawking doesn't believe him, and so goes to disprove him, and does the calculation, and finds out that in fact this is unexpectedly exactly what the answer is. In fact figures out that there's a factor of 4 at the bottom there. It doesn't just turns it from being a tilde into the exact answer. So this is in fact exactly what the answer is. This is the Bekenstein-Hawking entropy of a black hole.
One paper or 2 papers?
There was, in terms of what?
Like how many, I mean, did they write a paper together or separate?
No, very much not. Bekenstein wrote there was the Hawking area theorem, and then other people have been like, oh, this is a bit like thermodynamics, but had never really nailed it. And then Bekenstein wrote this formula down with a tilde, and then Hawking wrote this formula down exactly and figured out where the factor of 4 is.
Bekenstein had the order of magnitude as well, though, because he had this very weird argument about nice argument about kind of the minimum amount which you could raise.
Right. Yeah, so what I haven't done is there's all sorts of thought experiments to do with lowering boxes full of radiation down really close to the black hole and then dropping the boxes of radiation in, and those are super beautiful thought experiments that would also help convince you that this story had to be right. But I won't go into them in the interests of giving Jonathan some time. But those are super beautiful stories. So,
sorry, in classical thermodynamics, entropy has units, right?
No. Well, okay. You mean KBs and stuff?
Yeah.
Yeah. Okay. KB is definitely 1 in my units. So, yeah. Okay. There we go.
Or 1.
Yeah. Okay. I mean, I'm KB in here, but I'm not going to do that. I mean, that's where I would go. Okay. So this is in fact the most profound fact that we know about quantum gravity, is the fact that the entropy of a black hole scales like its area. And in fact, we now think that every event horizon you have, the entropy of that event horizon scales like the area. And as I said, the reason that's sort of surprising is that it's not extensive. It's not really clear what it means to put 2 black holes next to each other, but it doesn't go like r cubed. And this leads to something called the holographic principle that I will explain in a moment. And then I will hand over. And the idea is this. I guess there's one other thing after this I need to say before I hand over. The idea is that it had better be the case, if you don't want to violate the second law of thermodynamics, that not only is this the entropy of a black hole that fits in a given region, it had better be the case that nothing else you can put in that region has an entropy bigger than the black hole that you can put in this region. Because if you did have something else that could fit in that region, that had an entropy bigger than the black hole that could fit in this region, then I can violate the second law of thermodynamics in the following way. All that stuff that's in that region, what I'm going to do is I'm going to take bricks or whatever else, and I'm just going to throw those bricks into that region as well. And I'm going to keep doing that until the whole thing is now so heavy that it undergoes gravitational collapse and forms a black hole. That's apparently something I can do. And in order that that process not lower the entropy, it had better be the case that whatever else is fitting in that region is does not have a entropy larger than the black hole that I'm going to make. And so the entropy bound is that this is the entropy of a black hole that fits in an area, a region of area r squared. But I better not be able to cram through any other means more entropy into that region than r squared. So this is in fact a bound, that the total amount of entropy you can fit into a given region is bounded by its area. And in fact bounded by that formula. And that's really surprising. And the reason it's really surprising is that it scales like r squared. Here is a way that I can violate this bound, or at least you're going to tell me what's wrong with this thought experiment. I'm going to take a pile of Seagate hard drives, and I'm going to make that pile bigger and bigger and bigger. And the total amount of information you can store on a external hard drive is 1 terabyte, let's say, per certain linear size. And I'm just going to make that bigger and bigger and bigger, this pile. And maybe 1 terabyte per linear size is not very big, but it's clear that the entropy of the pile of hard drives scales like r cubed. And so if I just make r big enough, that's going to beat the r squared growth. So a big enough pile of hard drives can violate this bound. Is that right? Yeah, good, it's wrong. And what goes wrong is that, in fact, long before this pile of hard drives is able to violate the area bound on the entropy of a black hole, the whole pile of hard drives undergoes gravitational collapse and forms a black hole of its own. And so that is, in fact, the way in which you guarantee that this bound is tight, and there's no way to violate it. And that turns out to be what saves you if you try and violate it in the manner that I suggested. Yeah, you can't make them light enough, right? Yeah.
What if you try to apply the bound to the whole universe?
You can do that too, yeah.
But if we, like in the models where the universe is homogeneous, then if there's some entropy per unit volume, then we violate the bound for sure.
Our universe is only of finite extent in terms of our horizon volume is only of finite extent, according to the thing. Okay, there's a question of whether you're applying it to the universe or the multiverse. Applying it to the multiverse, I'm not going to go there, but there is a story in which that'll work out. If you're just trying to apply it to our visible universe, there is a finite total area of the universe. That's a kind of advanced question. That, as I said, these questions are always slightly harder in cosmology than in black hole physics, but there is a good answer to that.
Some people would argue that you don't need to impose a bound. Like that, you know, underworld debate is effectively that. Do I need to impose an additional bound on matter? It's not quite that one, but it's, there's like,
yeah.
Can I make, I think people would say if you did have hyperentropic objects which violated that bound, then yes, you try and create the black hole and it evaporates so quickly that you don't do it. So I don't think one needs to impose by hand an additional bound.
Those debates are mainly about the question of whether there's another bound that's a stronger bound than that people debate, which is whether this is also true, that if you have a certain energy within a certain linear size, whether you get a bound like that. And those debates are mainly about this stronger version. This I think is pretty secure.
Isn't there these
Okay.
like Morove and maybe this is a side tangent, but there's a bunch of these things on hyperentropic objects which I thought were about this one as well. Where if you have objects which are so entropic that they would violate this thing, when the black hole effectively evaporates much faster because they have a high cross section, so you don't create the black hole by.
That I think is not going to be right, because I could always take a black hole big enough that I wouldn't. I think that applies to this other one. But anyway, this is a sort of advanced topic, and let's not get sidetracked. Okay, so what does this mean? This means that if you have a quantum gravitational theory, like a black hole, it's sort of equivalent to, and it takes up some volume, it's sort of equivalent to a non-gravitational theory that that lives in one fewer dimension. that lives on the surface of the black hole, not inside the black hole. Why? Because you know that for non-gravitational systems, the entropy scales like the volume, or like the r to the whatever dimension of the system you have. And so you have a three-dimensional black hole that's a bit like you have a non-gravitational, whose entropy scaling is a bit like you have a non-gravitational system in one fewer dimension. And so this is sometimes called the holographic principle. That if you have that quantum gravity eats a dimension, and there are fewer dimensions than you thought, there were fewer degrees of freedom than you thought there were, because if you tried to excite all the degrees of freedom at once, you'd find you couldn't, because you just end up collapsing to form a black hole. So this is called the holographic principle, that a quantum gravitational theory in n dimensions is a bit like a non-gravitational quantum theory in one fewer dimensions. And in fact, this was the holographic principle that was sort of advanced as a profound fact about quantum gravity. And the holographic principle has recently found concrete instantiation in this ADS-CFT conjecture that I was talking about. ADS-CFT is a non-gravitational theory, quantum theory, which is what the CFT bit is. And you have a gravitational theory, which is what the ADS bit is, a quantum gravitational theory. And the CFT has fewer dimensions than the ADS, thus sort of instantiating the holographic principle. These are two theories that are meant to be exactly equal to each other. Yeah?
But in your black hole collapsing, I mean, it's only like part of your gravitational theory that changes, right? I mean, the rest, like, we are unaffected by that. It's just like the black hole over there. So it's like only like a small part has this.
Yeah, in the black hole case, there's the black hole entropy and there's the entropy of the rest of the stuff. In ADS-CFT, there really is. It's just one. It's like the theory of a black hole.
So, like, I mean, how do you? I think it also goes back to my earlier questions about this counting the entropy, etc. You sort of have these two things now, right? You have like the normal stuff like us,
yeah,
gravitating, and then you have these black holes that have this thermodynamics with a dimension less.
But at any moment, someone could try to assemble stuff around here into a black hole.
Yeah.
And then this would need to apply.
It's not like the entire gravity theory got a dimension lower. Right?
Yes.
I'm missing something.
It is like in the region where the gravitational effects are strong, it is like you lost a dimension for the black hole.
Only in that region.
Only in that region, but yeah, right.
Physics. So if you start forming a black hole right here, these properties would emerge. As you try to push the entropy higher and higher, you would start obeying this. Temporarily, it would look like a box of gas, blah, 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 but as you push past it harder and harder, you would start obeying those rules.
Okay, and there's just one more thing I wanted to say, which is that there is if you know what the entropy is, you know how to calculate the temperature. Thermodynamics just does not work unless you have the following formula being true. And so you can calculate what that is, and that's going to give you h bar over r. If you combine this formula and that formula for the entropy, and in fact with some prefactor, I think it's 1 over 4 pi. So this tells you that as well as having an entropy, black holes must have a temperature. This is called the Hawking temperature, and black holes radiate with this temperature. You have heard that nothing can escape a black hole, and that's true classically. When h bar equals 0, the temperature of a black hole is 0. But quantum mechanically, they give out a very, very small amount of radiation. The radiation is inversely proportional to their size. So very large black holes are very cold, small black holes are hot. If you have a black hole, a solar mass black hole, this temperature comes out to 60 nanokelvins. So it's extremely small temperature, impossible to experimentally observe. If you have the black hole at the center of our galaxy, that's 1,000,000 times colder still. But something very interesting happens, which is this means that black holes have negative specific heat. the smaller they get, the hotter they get. It's quite unlike the less energy they have, in other words, the hotter they get. That's quite unlike a box of gas.
But like any other gravitationally dominant
But
system.
yeah, like any system which is dominated by attractive forces, that will be true. And what that means is that if you have a black hole alone in an otherwise empty universe, it'll give out radiation, and as it gives out radiation, it will get hotter. It'll shrink a little bit, and then get hotter, and then as it gets hotter, it gives out more radiation, and there's a runaway process that eventually will lead to the entire black hole just disgorging itself back into the universe in a time that scales like its mass cubed. And this is a very long time for a reasonable sized black hole. A solar mass black hole takes a time 10 to the 55 times the current age of the universe to evaporate, it's called. But it's only polynomially long. It takes a polynomially long time to evaporate. So it's sort of quite... I guess that's something that never even occurred to me that was funny before. But
it's those constant factors that are killing you.
Yeah, it's